Now we come to the application of fluid mechanics. The charm of and the joy of the subject fluid mechanics is that we see a large number of applications and development of devices that are used for use of mankind for their facilitation, and in a large number of variety. Fluid mechanics is widely used both in everyday life activities and in the design of modern engineering systems, from vacuum cleaners to supersonic aircraft. To give you a very simple example, consider the ballpoint that we used for writing. Have you ever given a thought that when we are writing with a ballpoint, precise amount of ink is delivered by the pen as we write, not more, not less. If there is an anomaly, if it is not proper amount of ink, there is something wrong. But in most cases, it is okay. So, what is involved? A precision of engineering is involved in as simple a thing as ballpoint, but similarly, it can go to very complicated things, as we will see. Fluid mechanics plays a vital role, for example, in human body. And to give you examples for that, the heart is constantly pumping blood to all parts of human body through the arteries. The flow of blood that passes through our veins and arteries, whether it pumps out or pumps in, both cases, then what is it? The fluid laws are involved. So when there is a problem, we try to see that how to care for that. And that is why among scientists, there is a large interest, particularly these days, because a lot of heart problems are occurring. So scientists want to see and investigate the phenomenon of blood flow through arteries and veins, and to see how does it affect human bodies, how can we improve it, how can we regulate it, and how it deteriorates. So if we know all these things, we can look for solutions as well. Similarly, lungs are the sites of airflow in alternating directions. And as we all know, that all the air that we inhale goes to the lungs, and oxygen is separated from there. The carbon dioxide is exhaled, whereas the oxygen is then supplied to the body and the cells and so on. So all this involves fluid mechanics, rules and regulations, and so on. All artificial hearts, as a result, breathing machines that we use for saving lives in hospitals, dialysis systems, and a lot many more things they all use fluid dynamics knowledge. And so therefore, these subjects makes it very interesting that it is applied to human body. It is applied in many directions, as we will see. It has many application areas. Another example, an ordinary house, in some respects, an exhibition hall, for example, is filled with application of fluids. What are those applications? The piping systems of cold water. There is gas that is coming out, they're being provided to the house. There is a sewage system. Individual house and the entire city are designed primarily on the basis of fluid mechanics. So you can see earlier we gave you an example of human body. Here is an example of a house, ordinary house. But then you can take similar example to for example, an industry, a factory, any other location, the whole city, the water system that is being provided to a particular city or locality. Similarly, the same is also true for piping system and the network, heating, air conditioning system, and so on. Another utility, a refrigerator that involves quite a few tubes through which the refrigerant flows the compressor and pressurizes refrigerant, and two heat exchangers where the refrigerant absorbs and rejects heat, and as a result it cools the whatever the contents we place in the refrigerator. So you can see in household applications, other than the house itself, there are things that are being used by using fluid mechanics. Fluid mechanics plays a major role in the design of all these components that we have mentioned. Even the operation of ordinary faucets is based on fluid mechanics. We can also see numerous applications of fluid mechanics in, for example, automobiles. All components associated with transportation of the fuel from fuel tank to the cylinders, the fuel line, fuel pump, fuel injectors, carburetors, mixing of fuel and air in the cylinders. So you can see all this is quite complicated, intricate engineering, but it involves laws of or the knowledge of fluid mechanics. So again, what are we mentioning here? We are talking about the application areas of fluid mechanics. Then the combustion gases that are being exhausted, that is also very important. How much gases have to go out and what is important, how to make sure that the unrequired gases are exhausted from the vehicle. Fluid mechanics is also used in the design of the heating and air conditioning, the hydraulic brakes, the power steering, automatic transmission, and lubrication system. So you can see that how many things I have just counted, and they are all being applied, are they used at a given time in automobiles. And of course there are other vehicles also where this is used, but you can see that here also, and we use it every day, and we have never thought about it, that how this was designed and how perfect it has been designed, and if something doesn't work well, what was the fault, what is the deficiency, and why that happened. And if some machinery is doing well and works very well, then what are the good things about it, and what are the bases that it works very well. The cooling system of the engine block, for example, including the radiator and the water pump and even the tires. We fill tires with air, it gets heated as the vehicle runs, and similarly the water also gets heated. The engine, it's very important that we need to cool it down. So there is a system, if you see, that cools the engine part at the same time, and for that we used fluid flow. The sleek streamlined shape of recent model cars is the result of efforts to minimize drag by using extensive analysis of flow over surfaces. When the flow, as the vehicle is moving, there is a opposing flow of air that opposes it, and that created heat, resistance, what we call as drag, and so on. So the best thing, so that the fuel is consumed as little as possible and we can economize on things, the design of vehicles are made in such a way that the drag is minimized. And that is why the point that has been made, that the sleek design that is made is to reduce the drag. On a broader scale, fluid mechanics plays a major part in the design and analysis of aircraft, boats, submarines, rockets, jet engines, wind turbines, biomedical devices, the cooling of electronic components, and the transportation of water, crude oil, and natural gas. So you can see that there is no shortage of things where the fluid is not being applied. Fluid mechanics is not being applied. And that makes it interesting that we should somehow, study it, and that makes it interesting that not only to study it, but to apply it, and to apply it all these applications and improve them, make them more efficient and less costly, and so on. Numerous natural phenomena such as the rain cycle, weather patterns, the rise of groundwater to the top of trees, winds, ocean waves, and currents in the large water bodies are also governed by the principle of fluid mechanics. So earlier we were talking about the devices that we make, and to make them efficient, to improve their efficiency, and to at the same time economize on them. Now here are a large number of examples where the phenomena is happening naturally. We haven't designed it, but it happens. And some of the examples like rain cycle, the weather patterns, the rise of groundwater which vaporizes into the atmosphere, and so on, all these things are happening naturally, and all of them in some ways use fluid mechanics. Either use or fluid mechanics, it can be applied to them to analyze the system, and this is very important. So we shall be discussing them at later stages in detail mathematically.